Good morning, class. It is Thursday, April 16th. Before I start the lecture, I would like to point out a couple things that are coming up. First thing, homework number 9 is now available on my math lab. You have until May 5th at 11:59 p.m. to complete homework number 9. Also on May 5th is test number 4, and we will conduct that the same exact way as we did test number 3. For today, I decided, because today's lecture is very wordy, as you'll see, I'm going to count today's NTS as also lab number 7. But you're going to get 2 separate grades for these. So the NTS grade will be the usual grade that you've been seeing, and it's just a pass or fail grade. You do it or you don't. And as long as it's decent, I'll give you the credit. But for lab 7, I'm actually going to grade it. So you'll have 2 separate scores, but it's one assignment. So the NTS will be pass or fail, and lab 7 will just be a 10-point grade like all the other labs are. So please do a good job so you get a 10 out of 10 for lab number 7. So don't be lazy and leave things out or cut corners. So make sure you write down everything, the examples, the definitions. So make sure you provide detail and notations, all right, like a good student. I would really appreciate that. And so would your grade. And finally, I still don't know about the final exam yet. As soon as I hear anything from Collin College, I'll let you know how we will take our final exam. So today's lecture is going to continue inferential statistics, which remember is a branch of statistics that is concerned with making conclusions or generalizations about a population. And today we will be focusing on hypothesis testing. And I'm going to make this a 2-part lecture. So the first part is going to be looking at how do researchers determine the number of people that they need for a survey, or the number of people that they need for a study or an experiment in a lab or a hospital or for a psychological study. How do they know how many people they need? They don't guess. They actually have a way that they can calculate how many people they need for their study so that their statistics are reliable and dependable. So that's the first part of our lecture here. So what we're going to do is take the information that we learned from confidence intervals on Tuesday, and we're going to extend that to this, because we can take those formulas for confidence intervals and actually solve for how many people we need in the sample for statistical testing. So one of the confidence intervals that we studied was on population proportions, finding a percentage that represents a population. So recall that the margin of error for this type of statistic is given by this formula. And what we're going to be interested in is finding what n is. And notice that n is tucked away here in this square root in the denominator. So I'm going to have to solve this formula by rewriting it using some good old algebra to solve for n. But before I show you the steps to this, I'm just going to let you know that I'm dropping alpha over 2 here, and I'm just going to call this z, just for simplicity's sake. Okay? So what's the first thing I would have to do here? What I could do is, how about we isolate the square root by moving z over to the other side? So I'm going to divide both sides by z, and then I get the square root. Now what would the next step be? We're trying to get to n, so what we'd like to do is eliminate the square root. So I'd have to square both sides. Squaring both sides will cancel out the square root. Now n is upstairs, so what I would like to do is now flip both sides around. I'm going to take the reciprocal of both sides of the equation so it balances. So notice e over z becomes z over e, and this side also flips around. And then my final step is just to multiply both sides by my denominator. So if I multiply both sides by my denominator, p times 1 minus p hat, then I'll get n by itself. So this is the formula that we're going to use to find the number of people that I need in a study when I want to estimate a proportion. So let's talk about the formula. So this final formula depends on knowing the values of the margin of error, a z-score, and also p hat. So the margin of error can be set ahead of time. The researchers might say, I want no more than a margin of error of 2%. Usually a small percentage is a fine margin of error. Z is just determined based on the level of confidence you wish. So if you want 95% confidence, remember we have a table to find the z-score for that. So, these two things can be determined ahead of time. P hat's a different thing. So E and Z will always be known ahead of time. Sometimes we'll have preliminary values of P hat. And that just means there might be previous studies where they have this value available. But if it's not available, then what we're going to use is 50% for it. So 0.5 is a fair guess. Because don't forget, when a probability is 50%, we call that a fair probability. So when a percentage is unknown, we'll just use 0.5 as a rough estimate of what we think it could possibly be, because it's a fair number. But if P hat is known, that's because it comes from previous studies that we can draw from and use that as our estimate. And then the final thing about this formula is that you'll always round up. No matter what the decimal is, always round up. So this is going to go against the rules of regular rounding. We always round up to the nearest integer or whole number. So here's the example that goes with this first question. So suppose you want to estimate a proportion with a 3% margin of error and 95% confidence. How many individuals should be in your study? So we're going to do this two ways. We're going to say, okay, well, we don't have any previous information, so P hat is unknown. And then we're also going to say, okay, well, what if there was a previous study that found that P hat was 32% or 0.32? So one other thing I need to do is just identify some of the numbers that are in the example here. So first, the margin of error is right here, so it's 0.03. And then from my table, 95% confidence, the z sub alpha over 2 was 1.96. So part A, if P hat is unknown, what are we going to do? We're going to use 0.5. So then using the formula that I just gave you, all right, so this is the formula here, we're going to plug in our 0.5, 1 minus 0.5, and then z over e, so 1.96 over 0.03. Don't forget to square that quantity. And then on the calculator, you're going to get 1067.11111 repeating. And remember, the rule here is to round up to the nearest integer, which would be 1,068. So this particular study would need 1,068 people for the study to be able to achieve a margin of error of 3%, to achieve 95% confidence in that particular study. Now, if P hat is known to be 0.32, so now we still use 1.96 and 0.03. They don't change. The only thing that's changing is right here. P hat is known to be 0.32. So don't use 0.5 this time. So then the calculator gives you this value, and then you round up to the nearest integer. This study would require 929 people. The second part to this now, okay, well, what if we were trying to estimate a population average or mean, mu? So recall that the margin of error for this is t sub alpha over 2 times sample standard deviation s divided by the square root of n. So here we're going to do the same exact thing. We're going to solve for n using a little bit of algebra. So first thing I'm going to do is I'm going to multiply this time both sides by the denominator, because the denominator contains n and it's already separated with the square root. So if I multiply both sides by the square root of n, that stuff cancels over here on the right side. And then that gives me radical n times margin of error equals t times s. And then I'm solving for n. So now I'm going to divide both sides by e. All right, so I'll move that over there. So I get t times s over e. And then to isolate n finally, I square both sides, and I get this expression here. So n will be t times s over e squared. Now let's talk about this formula. There's a problem with it. And having a t-score in the formula is actually a problem. It's an issue. Why is the t-score an issue? Well, remember that the t-score chart that we used, the rows depend on the degrees of freedom. So to get a t-score, you need to know the degree of freedom, which is n minus 1. That's a problem because if we're solving for n, that means we don't know n. So how are you going to find the degree of freedom? So if you can't find the degree of freedom, that means you can't get the t-score, because the t-score relies on the degree of freedom, which depends on knowing the sample size. But if you're solving for the sample size, then this part can't be done. So then what we do, instead of t, we replace it with z. Because don't forget, when n gets large enough, t-scores become z-scores. So z-scores and t-scores are nearly the same when n is large enough. So z-score is a good, convenient replacement. So therefore, the sample size for n is now determined by, now the only difference here is I replaced t here. So this is z times s over e squared. Okay? So the formula changes a little bit because of that. And of course, just like last time, please round up to the nearest integer or whole number. All right, so this is the example that is also part 2 of your NTS and Lab 7. So we have here a recent Gallup poll asked Americans to disclose the number of books they read or read during the previous year. Initial survey results indicate that a sample standard deviation of 16.6 books. How many people are needed for a new survey to estimate the number of books read in the previous year within 4 books with 95% confidence? Okay, I would highlight some things that we know from this information so far. And here it is. So first, the sample standard deviation there is S equals 16.6. A, for part A, within 4 books. So whenever you see that term within, that's always a Q word for margin of error. So the margin of error here is 4, okay? And the z-score just comes from the table that you already have. So z is 1.96 for 95% confidence. So now, using the formula I just gave you, it's z times s over e. So plug that in, square it, you get this number, and we round up to the nearest integer. So this study would require 67 participants to achieve 95% confidence and a margin of error of 4 books. Now, what if we change it slightly to where we want the margin of error to be within 2 books, but still maintain 95% confidence? So what you're going to do is you're going to change E from 4 to 2 and just keep everything else the same, because we're still using 95% confidence. So just by changing the error there, which is your denominator, change that 4 to a 2, recalculate, and it gives you this number, which means we need 265 people for this particular study. Question C, what effect does lowering the margin of error have on the required sample size? So remember, the margin of error is decreasing. So that means we're going to create a narrower interval for estimating our population parameter. So if you have a narrower interval, you better be sure that a narrower interval is pretty accurate. And with data, you can become more accurate by increasing your sample size. So notice that by lowering the margin of error, it requires a larger sample size, right? Because in this problem, the margin of error was lower, but we got a larger sample size of 265. In question A, the margin of error was higher, it was 4, but we got a lower sample size. So by decreasing that margin of error, you need more people because you need it to be more accurate if the interval is more narrow. So having more people and more data will make it more accurate. Okay, so now I would like to talk about hypothesis testing. This is where it's going to get really, really wordy. There's lots of definitions and lots of things to write, so hang on. So first, in statistics, a hypothesis is a statement regarding a characteristic of one or more populations. So in other words, a hypothesis is just saying something like the mean of the population is 20, or the percentage of people that do this is 10%. So it's a statement that is very generalized about your population that usually includes some type of statistic, okay? Now, hypothesis testing is very much like a scientific experiment. So you'll see, as we continue on with hypothesis testing today and the next 2 weeks, actually, hypothesis testing is going to carry on over the next 2 weeks. You're going to notice it's very scientific in its method, where you need hypotheses, you need data, you have to analyze it, and then you make your conclusion. So it's really a scientific procedure that uses sample data to test the statements or the hypotheses regarding your population. And the 3 steps we're testing is this. So like any scientific experiment, you need a hypothesis. So you have to make a statement regarding the population. Now, either this statement or its opposite is true, right? So if the statement isn't true, then that means its opposite is true. If the statement is false, then the opposite is true. So in other words, in a hypothesis test, you need two hypotheses. So for example, suppose that someone makes a claim that the percentage of students in Collin College who read for leisure is 35%. Okay, so that's a proportion. So they would be making a statement that the p-value is 35%. What's the opposite of that? Well, there's a couple ways you could state the opposite. You could say that the p-value is simply not 35%. Or you could say, I think it's less or I think it's more. So that's why we need two hypotheses, because you're able to weigh the statement that is made against the opposite of the statement. So you can determine which one is more true. So two hypotheses are needed. So of course, what do you do to do that? You need to collect data to test it. And then C, you need to analyze whether or not to reject the statement that was made. Part C, the two hypotheses that are needed for testing. So remember, we need two hypotheses. We need a statement and its opposite. So first, there's what's called a null hypothesis, and it's denoted as H sub 0, or what people read it as H naught, or people just call it H null, because naught and null have the same meaning. Now, this will always be a statement with an equal sign, that the mean equals 5, or the percentage equals 10%. So it's always a statement of equality. And more specifically, when we say that two things are equal, we're stating that there's no difference between them, that there's no effect, there's no change. So in other words, when we say that two things are equal, it's a statement of the status quo. Remember, status quo means it is what it is. It's also, the null hypothesis is assumed true at first, unless your statistical evidence suggests otherwise. Also, it's because we're assuming it to be true at first. Remember, in statistics, when we talk about like bell curves, our true value typically should be in the center or near the center, somewhere near it. So we also assume that the null hypothesis, since we're assuming it's the true value or the status quo, we expect it to be near the center. The second hypothesis is the alternative hypothesis, which is denoted two ways depending on books. Sometimes, like I like to use H sub A because it makes sense, H alternative, but some will use a number. So if the null hypothesis is H sub 0, then the alternative would be H sub 1. Now, it's a statement that we are trying to support, because if the null hypothesis is already the status quo, then the opposite is what we're trying to show is either going to be supported or not going to be supported. And this statement will always be the opposite of the equality. So it's going to be a strict inequality statement. And these are the three types of strict inequalities that we use in mathematics. Not equal to, less than, greater than. So there are three ways to set up the null and alternative hypotheses. And it all depends on which inequality you are using for the alternative hypothesis. So typically we would write down our two hypotheses like this. We would have them lined up where you have your null hypothesis is that your population parameter equals some value. So that could be that the mean is 5 or the mean is 90, whatever it is. Then the alternative would be that the parameter, well, it's not equal to some value, but it might be less than some value. Another possibility is, well, instead of less than, it could be greater than. And the third possibility is, if you don't know if it's less or greater, you just know it's not the same, then you just state equals versus not equals. Now, going back to part A. So when we say that the alternative, that the null hypothesis equals some value. Now remember, we put that remember, we're assuming it to be true, meaning it's near the center. So my h sub 0 will go somewhere near the middle. And then for HA, the alternative hypothesis, if we're assuming that the parameter is less than some value, then that means it's going to be somewhere on the left side of this curve, of this bell curve. So we shade it in a little bit just to distinguish it from H0 or H null, and then we label that with HA. Similarly for part B, so H0 would go near the middle because of the equality. And then for the alternative hypothesis, if we're assuming our parameter is higher than some value, then that means it's going to be somewhere over here possibly on the bell curve. And then for part C, again, HO will go in the middle. And if we're assuming, excuse me, that the parameter is just different from some value, meaning it's just not equals, then that could imply two things. If it's not equal to the value, then it's either lower than it or it's higher than it. So we label both sides to represent that HA could be lower or it could be higher when it's simply not equal to the null hypothesis. Now we give each of these a specific name because this type of sets of hypotheses creates what we call different types of tests. So the first one's called a left tail test because remember that we're trying to test whether or not to support the alternative hypothesis. So because the hypothesis is in the left tail, we call it a left tail test. And then for the second one would be a right tail test, and the last one's a two tail test. So for example, so suppose we have the Medco pharmaceutical company has just developed a new antibiotic for children. 2% of children taking competing antibiotics experience headaches as a side effect. A researcher for the FDA wishes to know if the percentage of children taking the new antibiotic who experience headaches as a side effect is more than 2%. So what we're being asked to do here is to determine first what are the hypotheses of this problem and what type of test would it take. So first, because the statistic there is a percentage, we're going to be using P as our parameter. And then, so first, because the parameter there is P, remember that null hypothesis is always a statement of equality. So no matter what this says right here, we've just first start off by saying that the parameter is 2%. Because that's also stated up here in the second sentence, that the FDA is trying to prove against. So that 2% of children experience headaches as a side effect. So that's your null hypothesis. So here, when we say more than 2%, that's the alternative hypothesis because it's a strict inequality. So it must be the alternative hypothesis. So therefore, because the alternative is a greater than sign, more than, that means the alternative is going to be on the right side of the bell curve. So therefore, it's going to be a right tail test. For B, we have the Blue Book price of a used 3-year-old Chevy Corvette is $86,012. Grant wonders if the mean price, so focus on that, mean, it's a statistic, is different from what is stated. So he's wondering if the mean price is different from $86,012. So first, because it's a mean, the parameter that we're going to be using is mu. And what would the null hypothesis be? So remember, the null hypothesis is always a statement of equality. So we just take mu and this number and put an equal sign in between them. So there you go. There's the null hypothesis. What would the alternative be? So which inequality would I use when Grant wonders that if the mean price is different from this? Well, he doesn't say less. He doesn't say more. He says different. So that's when we use not equals. And that would be a two-tailed test. Because again, it could be less, it could be more. Either way is different, so it's a two-sided or two-tailed test that we would be using. For part C, we have the standard deviation. So of course, standard deviation right off the bat, remember, is sigma for the population. So the standard deviation of a bottle of detergent using an old filling machine is 0.23 ounces. The manufacturer wants to know if a new filling machine has less variability. So first, what's the null hypothesis? The null hypothesis would be that the sigma equals 0.23. Because remember, the null hypothesis always has an equal sign. And then, of course, less variability would mean the alternative would be that sigma is less than 0.23. So that means your alternative hypothesis will be on the left side of the bell curve, which would require us to use a left-tailed test. Now, there are 4 possible outcomes of hypothesis testing. So once you go through your test, then you have to start looking at what the conclusions are to your hypothesis test. And there are 4 possible conclusions. 2 of them are correct and 2 of them are wrong. So first, a correct decision is rejecting the null hypothesis when the alternative is true. So if that's what you figure out, if the alternative is true, then you reject the other hypothesis, the null hypothesis. Another correct decision is the opposite. So if HO is true and you don't reject HO, that you've made a correct decision. So what else could I write here about this? Certainly we could say that HA is false, right? So if HA is false, then we would not reject HO. So that's exactly what this is saying also, and that's a correct decision. Okay? Now, one thing I want to point out here is the fact that we won't actually know with 100% certainty if these are true or false or not. Okay? So because we don't know if they're actually inherently true, then errors can be made if something else happens. So number 3. So what happens when you reject HO when HO is true? And remember that we really don't know for sure that HO is true. But your experiment, your data, might lead you to this conclusion. And that could be you might have a smaller sample size than needed. You may have made some errors in your calculations. There's many reasons why you can make wrong decisions in hypothesis testing. So rejecting HO when it was actually true. But remember, we didn't know that it was actually true. That's some truth that's out there that only God himself knows. Okay? So rejecting it when it is true is obviously a mistake. And we call that a type 1 error. So when you reject the null hypothesis when it was actually true is called a type 1 error. Now, we're going back to, remember the alpha value. The probability of a type 1 error is what we call alpha. And typically we want that to be small. So remember some common values of alpha were 1%, 5%, and 10%. Okay? And remember that went with levels of confidence. So if your probability of type 1 error is 5%, that means you have 95% confidence. Okay? So again, the probability of a type 1 error is, again, the probability of wrongly rejecting the null hypothesis because it was actually true, but you didn't know it. And also in statistics, this alpha value, or this probability, is also known as the level of significance. Okay, now the opposite here. Suppose HA is actually true, and only God himself knows it. You didn't know that in your experiment, but for whatever reason, your data, your decision-making led you to decide to not reject the null hypothesis. All right? But if you knew HA was true, you would have rejected the null hypothesis. But for some reason with your data, you concluded otherwise. So that's a bad decision. It's wrong. We call that a type 2 error. And here, the probability of a type 2 error is this symbol here. We call this beta in Greek. It's kind of like B in Greek. And that is simply the probability of doing this. What's stated in number 4. It's the probability of not rejecting the null hypothesis when, in fact, the alternative was true. Okay? Now, again, remember the whole idea with truth here is that you really don't know that it's true. All right? It's a truth that's out there somewhere in the cloud, in space. God himself knows it. You'll never know the actual truth. Okay, so for example, suppose a skydiving company advertises that their parachute failure rate is 0.01%, or in other words, 1 out of 10,000. That doesn't sound so hot. A safety inspector believes that the company's failure rate is actually higher. Interpret the meaning of type 1 and type 2 errors in this particular problem. Okay, well, in order to do that, you need your null and alternative hypotheses. So first thing we're going to do is we're going to set up the null and alternative hypotheses. So what would your null hypothesis be here? First, you have to look at what type of statistic is this? It's a percentage. So we're going to use P as our parameter. And for the null hypothesis, we use an equal sign. Always use an equal sign. So we're going to say, well, P equals 0.01%. It's the status quo. It is what it is, right? Now, for the alternative hypothesis, we're going to go with the safety inspector. He believes that it's higher, so we would use a greater than sign, that the percentage is actually more than 0.01%. Now, let's interpret type 1 error. So, remember, the type 1 error is when you wrongly reject the null hypothesis, meaning you wrongly support the alternative hypothesis, okay? So, what would happen there? So, if we wrongly reject the null hypothesis, right? So that means that gets thrown out. And we're believing the alternative is actually the case. But it's wrong, right? We wrongly support it. So the inspector would wrongly make the company look like that their parachutes fail to open more than they really do, right? Because this is the statement we're supporting, that it's more. But we were wrong with that decision. So what issue could that create? Well, that would hurt the company's reputation. You would probably file a report. You would probably fine the company for something that's not even true. And then, of course, the word would get out there that this company has a much higher failure rate than what they're advertising, and their business would go down. Type 2 error. So now, remember what that is that you mistakenly fail to reject the null hypothesis, meaning that you should have supported the alternative hypothesis, okay? So type 2 error is that you should have supported HA, but you ended up supporting H0 instead, okay? So what problem is that? You're saying that the company's claim is correct and that the inspector was, you're saying that, you're saying that the company's claim is correct, but you should have supported this. You should have supported that the rate was actually higher. So the inspector would wrongly take the side of the company by saying that they were correct, when in fact, the actual truth is that the parachute failure rate is higher. Well, what problem would that create? Well, you're not addressing a problem that is actually there. So if you're saying that the company was correct, there's no need to make improvements on the parachutes. But however, the truth is that the failure rate is much higher. So therefore, you're going to put skydivers at risk. Fatal risk, possibly. All right, E, stating conclusions in hypothesis testing. So now this is kind of going back to, the correct conclusions, the incorrect conclusions. But aside from the fact that whether they're correct or not correct, what conclusions do you make from that? So first, conclusions are twofold with sufficient evidence. So most statisticians, or all statisticians, usually make a statement that there's sufficient evidence to reject this hypothesis. There's sufficient evidence to support this hypothesis. Okay? So conclusions are twofold because you have two hypotheses. So you have to say something about both. So first, for the null hypothesis, we always say that we either reject it or we fail to reject it. So we never say it's true. We never say we accept it. All right? And here's why. Think of court verdicts. When you go to court, they never say, oh, congratulations, you're innocent. All right? They say you're not guilty. Or, if the tables are turning the other way, that you are guilty. So in court, they always say that you're guilty or not guilty. They never say you're innocent. So there's never a verdict of innocence. So what that means is that we can never prove a hypothesis to be true. And think about court cases. Court cases are just like hypothesis testing in statistics. So first, there's a hypothesis made, right? That the person is presumed innocent until proven guilty. Okay? So then the defense and the prosecution, they'll present evidence, and then the jury will weigh the evidence, and then they'll come back and say guilty or not guilty. So it's the same exact process of statistical hypothesis testing as it is in court. Now, for the alternative hypothesis, we use the word support or not support for concluding about the alternative hypothesis. So in other words, if you reject the null hypothesis, you will in turn support the alternative. Whereas if you do not reject the null hypothesis, you will not be supporting the alternative hypothesis. So let's go back to the skydiving example here and talk a little more about this. So suppose you reject the null hypothesis. What can you conclude? Well, remember, the null hypothesis was this, that the percentage is just 0.01%. And so therefore, if you're rejecting this hypothesis, you are supporting the alternative. So what can you say about this? Well, what does it mean that you're supporting this hypothesis here? It means that the true failure rate of the parachutes could be more than 0.01%. But also, be a good statistician and use that phrase sufficient evidence. So we would conclude that there is sufficient evidence that the parachute failure rate could be more than 0.01%. Never say that it is. Never say that it's true, because remember, it's never 100% certain. And remember, just like with court, you can never say that somebody is innocent. So here, the way we word it in statistics is that we're not saying that it's true. We're saying that it could be. All right. Secondly, suppose the null hypothesis is not rejected. What can you conclude? So again, it's always helpful to label your hypotheses once you make your decision. So label HO as not rejected, which means the alternative is not supported. So what does that mean? So to not reject the null hypothesis, that is in a sense what we are supporting. So we would say that there is no evidence to say that the parachute failure rate is more than 0.01%, because that's the thing that is not supported. So there's no sufficient evidence to support that. So therefore, the null hypothesis is what is being supported. So we would say thus, here's from the null hypothesis, that the failure rate could be 0.01%. Okay? And that is the end of today's lecture. So hopefully by 5 p.m. you'll be able to turn in the NTS. And remember that it will count as also Lab 7 and will be graded on a 10-point scale. So make sure you've done a good job on today's assignment. So that is all. Have a great weekend, and don't forget to complete homework number 9. Take care, folks.